Imagine a student who memorizes the answer key and then aces the exam. Impressive score, but did they actually learn anything? A machine learning model can pull exactly the same trick. Feed it enough capacity, and it will happily memorize the examples it was trained on, and if you then test it on that very same data, you'll be fooled every single time. The score looks spectacular and means almost nothing. Today, we're covering the train-test split, the simplest and most fundamental habit in all of machine learning. It's the discipline that keeps you honest about what your model can really do. So let's break it down piece by piece. So how does this actually work in practice? It comes down to a short, disciplined routine. You start by shuffling your data and slicing it into two parts. Typically 70 or 80% goes into the training set, and whatever is left, the other 20 or 30%, becomes the test set. The shuffle matters because you want each side to be a fair, representative sample of the whole. Then you fit the model, and here's the one non-negotiable rule: you fit it only on the training portion. The test rows stay completely out of sight while the model learns its patterns, as if they didn't exist yet. Once training is done, you evaluate the model a single time on that untouched test set. Because it has genuinely never seen those examples, the score you get is an honest read on real-world performance. And notice, you evaluate once at the end. Peeking at that test set over and over quietly leaks information and inflates your estimate. Often you carve out a third slice in between a validation set, used all through development to tune hyperparameters and pick between models. That way your precious test set stays completely sealed until the very end, when it really counts, giving you one clean, uncontaminated verdict. Now let's make the whole point crystal clear with a simple side-by-side. Grade a model on the same data it trained on, and pure memorization looks exactly like skill. The number climbs beautifully, you feel great, but it tells you nothing at all about how the model behaves on anything it hasn't already seen. You've measured recall of the answer key, not understanding. Hold out a test set instead, and you finally measure what actually matters: generalization to new data. Scoring on examples the model never once saw is the only honest gauge of whether it truly learned the underlying pattern or simply memorized the answers in front of it. All right, let's keep in mind the ideas that matter most whenever you split data. First, fit on the training set and judge on the held-out test set, always. The two jobs stay strictly separate because the moment they mix, your evaluation stops meaning anything and you're back to grading homework you already saw. Second, remember what you're really measuring here: true generalization rather than memorization. That gap between training and test performance is the honest signal you care about. Third, respect the pitfalls, because a careless split can quietly ruin everything. Shuffle unless it's time series, in which case you split by time, so you never train on the future. Stratify for imbalanced classes, so both sides share the same class mix. And scale using only the training set statistics, so nothing leaks into the split. Okay, let's lock in what really matters here. The practice fits your model on one portion of the data and evaluates it on a separate portion it has never seen. It exists because a model can memorize its training data perfectly, and testing on unseen examples is the only honest measure of generalization, which is really the entire point of machine learning. Watch the details, shuffle and stratify sensibly, add a validation set for tuning, and never let pre-processing leak test information into training. Think of this as the simplest guard against fooling yourself, with cross-validation as the sturdier, more robust version of the same idea. Want more machine learning concepts explain this cleanly? Head over to standarity.com and keep learning.